Okay, welcome to the first ACEMS public lecture for 2021, the mathematics of knots. Before proceeding, I wish to acknowledge the people of the Kulin Nations on whose land we are gathered today at Monash. Pay my respects to their elders past and present. And please note that this lecture will be recorded and made available on the ACEMS website, which is www.acems.org.au. And for those of you who are unfamiliar with ACEMS, ACEMS is the Australian Research Council Centre of Excellence for Mathematical and Statistical Frontiers. My name's Tim Garoni. I'm a Chief Investigator with ACEMS, and I'm the Deputy Director responsible for outreach. And I'm very pleased to be able to announce Jessica Purcell as our first speaker for this year. Jessica is a professor in the School of Mathematics here at Monash University, working in low-dimensional topology. Jessica completed her PhD in mathematics at Stanford University. She's the recipient of an Australian Research Council Future Fellowship, a Sloan Research Fellowship, and a von Neumann Fellowship from the Institute for Advanced Study at Princeton University. And she's also currently the Associate Dean for Research in the Science faculty here at Monash, but somehow still managed to find the time to come and give us this lecture. At the conclusion of Jessica's presentation, we'll be taking Q&A, so please make sure you put your questions in using the Q&A button on the bottom of your screen. And without further ado, I'd like to invite Jessica to speak to us about the mathematics of knots.
All right, well, thank you very much. Thanks for the invitation to give this presentation. Thanks especially to ACEMS. There's a lot of really great things for mathematics in Australia, and I really enjoy being able to support them in this way. So as said, I'm going to be speaking about the mathematics of knots. I'm going to jump into a story that you may or may not have heard. This is a legend about Alexander the Great. So around the 4th century BC, there was this massive knotted ball in the city of Phrygia. And an oracle had said that anyone who could unravel this knot, it was called the Gordian knot, was destined to rule all of Asia. So this had been there for a long time. Alexander the Great showed up, he took a look at the knot, and he pulled out his sword and he sliced it through, and it was unraveled, and he became the king of Asia. That's the way that the story goes. So this is a great lead-in into a talk about knot theory, except Alexander was not actually acting in a very mathematical way. So let me explain how mathematicians might have viewed this problem of the Gordian knot. First of all, what is a knot? This is the most important thing for this talk. A knot, the mathematical definition of a knot is it's a smooth embedding of a circle into three-dimensional space. So this picture over here on the left, this is a three-dimensional representation of a knot. Another way of thinking of it is if you take like a string, say your shoelaces or something, and you tie it up and then you weld the ends together to turn it into a circle, that makes it into a knot. Over here on the right, we have a mathematical representation of a knot. This is called a diagram. And you can see it's actually a two-dimensional thing, but you have these little gaps that indicate where the knot passes under itself. So these are the same pictures of the same knot. We're interested in when two knots are the same. So we say that they're the same if you can deform one into the other without cutting. So Alexander the Great got it wrong here. He was not supposed to cut the knot. He was supposed to just deform it. Shown on this slide are some legal ways that you can deform a knot. So these are all pictures of the same knot. Over here, you can twist this around. So twist this up to make a little kink. That's a legal way of deforming. You can pull this strand here up into the kink. That gives you this. You can twist around this 8 figure to undo it. That gives you this knot. And then you can slide these guys around to get this particular knot. So these are all equivalent. This is art by George Francis, I should say, from 1983. So these are all equivalent knots, equivalent ways to get the same knot diagram, or the same knot. Okay, so it happens that, remember, Alexander had this problem of undoing a knot, and he ended up slicing it. It may be, even though he wasn't doing the mathematical thing, he may have been doing the smart thing anyway, because there are infinitely many knots that cannot be unknotted without cutting. So we say a knot is unknotted if it's equivalent to this, just a circle with no crossings whatsoever. These are the two next simplest knots. This is called the trefoil with 3 crossings. This is the figure 8 knot with 4 crossings. So if it were the case that this Gordian knot was actually knotted rather than unknotted, then there would have been no way for Alexander to solve the problem without cutting it. This may or may not be a lesson that you should learn and use in real life. If your mother comes to you with a phone cord that's all knotted and you look at it for a while and say, you know what, I think this isn't the unknot, could I please borrow your sword? Okay. So big question, how do you know if a knot can be unknotted? This is the key question in knot theory, really. So the knot theory wants to know, given a picture of a knot, given a diagram, some sort of a representation, when can it be unknotted? And this is a hard problem. And there is a similar problem that's, I'd say that's basically another theme, which is how do you know if 2 knots are the same? So maybe you have 2 things that aren't the unknot, but how do you identify them as being the same knot? So these are the major questions that knot theorists think about. Okay, so this seems like a good place to throw in a few caveats on this talk for experts in the room. When I chose what to talk about, I decided that this talk would be made up of stories and questions and pictures. And I view myself as a curator of the best or my favorite stories and questions and pictures in knot theory. We're going to see on the next slide, knot theory is ancient. And so this talk is nowhere near complete. I've only got 40 minutes left at this point. So I'm not going to be able to tell you everything about knot theory. However, as I said, I'm going to pick some of my favorite topics about it. And the third caveat is that this talk is going to be mostly true, but there are going to be some technical details that I'm not going to be able to cover in full detail. Okay. All right, ancient knot theory. So as I said, knot theory is ancient. It appears in all cultures all across the world, dating way back. I've got a few examples here. These were taken from an article on knots in art published in 2012. The first one here is Chinese decorative knots. This is a picture from 960 to somewhere in this range of years AD. Greek jewelry from 300 BC. This is from an illuminated manuscript that was produced in Northumberland in the UK in the Middle Ages. You can see knots all over this picture. Tamil threshold designs. This is a region in India where these designs are painted on thresholds of buildings. So you can see that knots are old and appear in many, many places. So when does knot theory stop being art and archaeology and become mathematics? This is the oldest example of a knot that I was able to find in my Google searching as I prepared for this talk. This is a seal from Ur in Mesopotamia around 2600 to 2500 BC. You can see it's a snake. Here's the head, and it is knotted around itself like so. It goes over, under, all the way, it ties itself up. And eventually, blah, 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 blah. Here you get back to its tail, which meets up with the head at this point. Okay. So is this mathematics or is this just archaeology? Well, this looks remarkably like an example that I was thinking about in a paper that was published in 2016. So we called this thing an alternating weave. And you notice that if you connect the sides of this weave together, you'll get something which looks very, very much like this snake. This paper appeared in the Journal of the London Math Society, so it's definitely mathematics. So I would argue that this picture over here is also mathematics. Who gets to decide when it becomes mathematics? I'd say if there's symmetry and there's logic and there's attention to detail, these are all mathematical things. And since I'm giving the talk, I get to decide what's mathematics, and we're calling it all mathematics. Okay, so then you may ask instead, when did knot theory start looking more like modern mathematics and less like some of these patterns? And I guess that would probably be in the 1700s. So Vandermonde was a mathematician in 1771. He wrote a paper that referred to knots. You can see this quote. Gauss was interested in knots, and he passed that interest along to his student Listing, who was doing some work in the 1840s. This is a picture from Gauss's notebook in 1794. All right, but the person who really was the father of modern knot theory, I would say, is Peter Guthrie Tait, who's so important that he gets his own picture in this slide. Tait was a Scottish physicist, and he was playing with smoke rings in the late 1800s. His colleague, Lord Kelvin, watched the smoke rings, and he hypothesized, perhaps the atoms, the fundamental building blocks of the universe, perhaps these are knots. So Tait liked this idea, and he started classifying knots, thinking that he was building a periodic table of the elements, basically. Okay, so this is what Tait did. This is a picture of one of his papers from the 1800s, where he started trying to classify knots and to find what he called the first 7 orders of knottiness. And you can see there's a lot going on. This is actually only half of one of several pages that appeared in this paper. So that was pretty cool. And then this went on. Tait's work convinced other people to get interested in this. So this slide is basically kind of a who's who in early knot classification. I've mentioned Tait. After Tait started publishing his papers on knots, Kirkman got interested. So his first paper on knots was 1884. Kirkman was a vicar in the Church of England who did mathematics kind of on the side as a hobby. And when he was 78 years old, he started getting excited about knots. So he wrote that paper, and then he started collaborating with Tait. And Little was an American mathematician. So he was living in Omaha, Nebraska, and also thinking about tabulating knots, classifying knots. And he started corresponding with Tait, who wrote back, and Tait and Kirkman, they compared their diagrams, made some corrections. And by 1900, they had a list of knots with up to 10 crossings. Okay. Now, at that time, Little, the story goes, Little apparently sent Tait more diagrams and said, let's do 11. And Tait kind of backed off and said, no, that's enough for me. Not that interested. But other people kept it up. So Mary Haseman is somebody that I discovered very recently. She wrote a PhD at Bryn Mawr in Philadelphia in the USA in 1916, which is titled On Knots with a Census of the Amphichirals with 12 Crossings. And then this was published in 1918 in the Transactions of the Royal Society of Edinburgh. And from there was a little bit done. We'll say a little bit more about, there's this gap. I think people weren't as interested in making tables between them, but in 1969, John Conway, he completed up to 11 crossings with a few errors, and those were corrected, I think, by 1974, were the last corrections in these tables. Okay, so that's a little bit of, I wanted to show you a picture. This is Mary Haseman's thesis from the Transactions of the Royal Society, which I just thought that was very pretty. So the classification of knots has some very nice pictures. Well, okay, let's talk about what they did and what this looks like now. Knots up to 7 crossings have diagrams that look like this. So we've got the unknot. Over here is a knot with 0 crossings. There are no knots with 1 or 2 crossings. All of them are equivalent to the unknot. We have 1 knot with 3 crossings, 1 with 4, 2 with 5, 3 with 6, 7 with 7 crossings. You can see this is growing. More with 8 crossings, more with 9 crossings, 165 with 10 crossings. Okay, and this is what these tables look like. Okay, so here's a question you should be asking. How do you know that they're different? We've got all of these tables of knots, and how do you know that we're getting different knots out of this? And the answer is, sometimes you don't. This is a pair of knots with 10 crossings that appeared in the original work of Tate, that persisted for many, many years. And then in Ken Purcell in 1974, he realized that they're actually identical. So Purcell also has kind of a nice story. As an undergraduate, he did a lot of knot theory, and he was playing with different ways of distinguishing knots, and he found that he couldn't distinguish these two knots. He left that, he went on to law school, but he was still kind of interested in this sort of thing. So while he was a student in law school, he pulled out these two knots one day, and he figured out that they're actually equivalent. And so he wrote a paper, it's 2 pages long, published in the Proceedings of the American Math Society, with these two diagrams, or showing these two are actually the same. So that was kind of cool. Somehow this didn't get communicated extremely well to some of the people involved. So Dale Rolfson wrote a book on knot theory that was published in 1976, 2 years later. And Rolfson didn't realize that these were not the same, and so he included them as 10-161 and 10-162 in his book. So this was an error in Rolfson's book. Purcell wrote to Rolfson. Rolfson realized that was an error. He took out and in later publishing one of these, but it screwed up all of your knot numbering. And now if you go look on the web for the Purcell pair, you may be getting 2 distinct knots, or you may be getting the same one. It's very confusing. Anyway, these ones I've checked. They're the same. Okay, but how did people know how these were going? Or how did they do the work on this classification? Back in the early days, they used things like this, called Reidemeister move. They just took the diagram and they adjusted it. So you can undo a kink is one move. You can pull 2 strands past each other like so. That's another move. This one, you pull a strand past a crossing like so. That's all that these moves are doing. These were used in the 1800s for this knot classification, but it wasn't until the 1920s that there was an actual proof that they work, that they're doing what you think they're doing. So in particular, it was shown by independently by Briggs and Alexander and by Reidemeister that equivalent knots will differ by a sequence of these particular moves. So that's why they're called Reidemeister moves, after Reidemeister was one of the first people to prove that they work. They're doing what you think they're doing. Okay, so now we're going to have a little interlude. I have a series of slides here. We're gonna decide if we have a knot or an unknot. So this one is easy. This one uses Reidemeister move number 1. Notice there is a kink here, and our move says we can undo the kink and straighten it out. And when you undo that kink, you get the unknot. So this is the unknot. Knot or unknot. This one is also somewhat easy. This one uses Reidemeister move number 2. There's a whole strand here that you can pull past the whole strand here, and that becomes unknotted. So this is the unknot. All right, knot or unknot. Give you a second to look at that. This one is special. It has a name. This was discovered by Goritz in 1934. This is in fact an unknot as well. The special thing about this unknot, though, is this was the first example. This is the first example of knots that is an unknot. But in order to undo this diagram, you have to actually add more crossings before you remove them. So you've got to do Reidemeister moves, increasing the complexity, the number of crossings, before you're able to do Reidemeister moves, taking it down to the unknot. Okay, so it was hoped in the past that maybe you just look at the number of crossings on a knot, and then you can do the Reidemeister moves, and you can remove some, you could just decrease the number of crossings all the way down, and you end up with the unknot, if it is the unknot, but otherwise not. Not that easy. You may have to go up in the number of crossings, and you may have to go up a long ways, and then you may be able to come back down again. Okay. All right, here's one, knot or unknot. This one appeared on Oxford Maths Twitter in early 2021, so earlier this year. I'll say a little bit more about it later. Oxford Maths, they stated that this is the unknot, but it's not completely obvious to me, and I haven't checked it. Okay, here's my favorite. I found this one on an art auction website. This is a mid-century modern hanging wall spaghetti lamp fixture. So is this a knot or an unknot? I have no idea. It seems that in order to figure out if it's a knot or unknot, you may be ruining your art and your mid-century modern hanging ball of spaghetti. Sometimes maybe it's good just not to know and just hang it in your living room as it is, knot or unknot. The trick with this is you need to make sure that if you have visitors, you may have somebody come in who takes one look at the knot and says, I know exactly what that is, and they'll pull out their sword and slice it, and that'll ruin your living room decor. Okay, let's jump back to more discussion on Reidemeister moves. I mentioned that Reidemeister moves were used in the 1800s. It wasn't until the 1920s that it was proved that you really could use them. They were legal. It wasn't until 2001 that somebody thought to ask, well, how many Reidemeister moves do you need? We know you may have to go up. Is there a bound on how far you go up before you go down? And Haas and Ligarius found a bound. So they found an algorithm using Reidemeister moves to determine if a knot is an unknot. In particular, if you have n crossings in your knot, then we can determine if you have the unknots in no more Reidemeister moves than this number here. So what is this number? This is 2 times the number of crossings times 10 to the 11th. This is 100 billion. And then you take 10 to that power. So it will only take you this many moves. So it's finite. Just to compare this to some fun facts. There are about 10 to the 82 atoms in the entire universe. And the estimated age of the universe is 10 to the 18 seconds. So to put this number into perspective a little bit, if you took 1 second per Reidemeister move, then after about 100 billion seconds or 100 billion ages of the universe, you'd be able to tell if your single crossing diagram is or is not the unknot definitively. All right, so only a few 100 billion ages of the universe. Okay. Is there a better way? Yes, there is a better way. Yes, star, there may be a better way. Sometimes there's a better way. Knot theorists use knot invariants a lot. And so what is a knot invariant? Given a knot, it assigns a number or a polynomial or some sort of a mathematical object to the knot. And as long as equivalent knots have the same value, then you can use this value to determine whether or not these things are the same. So I'm going to give an example of this. I'm actually going to start with kind of a complicated example. This may or may not be the best way to teach this sort of thing, but historically, this is one of the first invariants that people used. So we're going to look at the knot group. This is being looked at in the 1905 by an Austrian named Bertinger and others. But the idea is, rather than looking at the knot, you look at the space around the knot. So forget about the knot, just look at what you can do in the complement of the knot, in the exterior of the knot, in the part of the space that isn't the knot. And to form the knot group, you look at all the loops that you can draw inside of this space. So here are 3 loops that wrap around the knot in different ways. I need to know that this is a knot invariant. So in other words, we'll get the same set of loops for the same types of knots. And you can prove this using different types of mathematics, but you can kind of also just visualize it by looking at the Reidemeister moves. The loops slide around the Reidemeister move. So like this loop here slides around the kink, and you only get 1 loop from this. And similarly, you get the 2 loops here and similar loops here. So this is in fact a knot invariant. The same spaces or the same knots will give you the same set of loops. So what is it with a group? You can take these loops and you can multiply them. So that's shown on this slide. If you have a loop here named A and a loop here named B, If you follow A and then immediately B, that's a new loop, and we call it A times B. And you can cancel loops. So this loop here is named C. If you go backwards along it, then you've canceled the loop. This is called inverses. Okay, so this is a little bit technical here, but a set that has a multiplication and an inversion and a couple of other properties, this is called a group. And this appears in a huge area of mathematics called abstract algebra. So this is good news. Abstract algebra is a massive field with lots of books written on it. This is a picture of my bookcase in my office of all of my algebra books. So you can see that people have thought about algebra a lot, people have thought about groups a lot, and we have just changed this problem of distinguishing knots from this really hard problem in looking at abstract things in space into a problem that we know, which is called abstract algebra. Okay, we can figure out knot groups of certain knots. Here's the knot group of the unknot. Turns out to be, the knot group is the counting integers, Z. And the way that this works, this is not really a proof. As I said, this is a mostly true talk. This is mostly a proof. But the idea is you just count the number of times that a loop will wrap around the unknot, and that will give you the counting integer. So how many loops are there in the space around the unknot? Well, there's one loop going this way. That's one. There's a loop going 1, 2 times around. The loop I've shown here goes 1, 2, 3 times around. There's another one going 4 times around, and so on and so on and so on. And in fact, it's a little harder to prove, but you can prove that there's no other knot whose knot group is Z, the counting integers. And so in order to distinguish knots, then all you have to, or to show that something is the unknot, you need to show that its knot group is Z. So here's another example, this 3-crossing knot, the trefoil. We can figure out its knot group. This is a picture that came from Rolson's book, Knots and Links. Here's the trefoil. You can put it on a torus like so, or on the surface of a donut. It turns out that there are 2 loops that are important in the knot group. One is called X, he's got it going this way. One is called Y, he's got it going this way. And because of the way the knot wraps here twice around one direction, 3 times around another, you get a relation X squared is equal to Y cubed. Okay, I gave a practice talk on this last night to my family, and my son said at this point that I had lost him. That's okay. The point is that you can take this new group and plug it into algebra. So whether or not you understand where the group came from, plug it into the algebra machine, turn the crank, algebra says, hey, this is different from the counting integers. So this is good news. We have just proved something important. We have proved that the trefoil is not the unknot. So let's go through this one more time. Why is it not the unknot? Well, if the trefoil is unknotted, then it would have to have the same knot group as the unknot. The unknot has group equal to the counting numbers. The trefoil does not have knot group equal to the counting numbers, so therefore they are totally different knots. So we have found our very first example of 2 knots that are different, the unknot and the trefoil. Okay, this is great. So does this always work? Can you always find the unknot? No, not really. So the problem is abstract algebra is also really hard. There's a reason there are all these books about algebra. It's because it's difficult to tell 2 groups apart. And so this method will work for some groups. It worked really well for the trefoil. It worked really well for the for other torus knots, but it doesn't work very well in general, unfortunately. Okay, so is there a better invariant? So remember, an invariant, it associates something with a knot. You get the same thing for the same knots, and you can tell some knots apart. Well, this is a difficult question to answer. So yes, there are some invariants that work better for certain problems than others. And there are some that are good at distinguishing different families. But there's nothing easy. Everything has a trade-off. The we know of invariants that distinguish every single knot, but these are usually very difficult to compute. And we know some that are easy to compute, but that don't do a very good job of distinguishing things. So there's always a bit of a trade-off. So if you remember, I said that in this talk, we're looking at stories and pictures. I've picked a few of my favorite invariants that have the best stories and the best pictures to tell you about during the rest of the time for this talk. Okay, so one of my favorite invariants is Seifert surfaces. The knot group is kind of a one-dimensional invariant. You take loops. These are one-dimensional objects that go around the knot. A Seifert surface is a two-dimensional invariant. So this is a surface that sits in the space around the knot and has its boundary on the knot, like so. But it's sitting in space. And so these pictures came from these two people, Van Wyk and Cohen, have found a way to visualize these surfaces. And if knots have different, well, there are different things you can do to look at Seifert surfaces to distinguish knots. Okay. All right, so that's a two-dimensional invariant. We've also looked at a one-dimensional invariant, the knot group. We should talk about a three-dimensional invariant. This is my favorite invariant, hyperbolic geometry. This is where my research lies. I really study a lot of hyperbolic geometry in relation to knots. And I'm not going to go, we don't really have enough time to go into a lot of detail about what hyperbolic geometry is, but the idea is that you can take this knot or this space around the knot and you can straighten it. It technically means you're going to put a metric on it, and often this metric has negative curvature. And then once you have a metric, you can use geometry. And different knots are going to have different geometry. There are going to be different lengths of curves. There are going to be different measures of volumes, things like this. So this is a picture of the figure-8 knot, what it looks like when you straighten it, when you're inside the geometry. And this was created by Gerner, Sagerman, and Schleimer recently. We'll come back to that in a second. So to explain it a little bit more, the figure-8 knot has a decomposition into two tetrahedra. This is due to William Thurston in the late 1970s. I've kind of tried to illustrate it here. It may or may not be successfully done, but the idea is you start with the knot, and then you have these faces of the tetrahedra. There are 4 faces of a tetrahedra, and they are shown here in gray and in blue. These are 2 of the faces. And then there's one in green, it's the outside, and then in a darker blue is the inside. These are 2 more faces. So those are your 4 faces. So if you put the 4 faces into the diagram and you kind of wiggle the diagram around, you can see how they fit. So the blue one here, the dark blue one here, the gray one, the green one. And then you shrink these little bits of diagram down to points. And that's where you can really start to see the tetrahedron. So the 4 faces become 4 triangles on the side of a tetrahedron. So there's this one that we've drawn is a tetrahedron on the front toward your head on the screen. There's also another one on the back with the same faces. And when you glue them together, you get the figure-8 knot. Okay, so that's kind of complicated. If you're happy with that idea though, the next step in giving hyperbolic geometry is you straighten the tetrahedron in hyperbolic geometry in 3 dimensions. And over here on the left, I've got a picture of a 3-dimensional hyperbolic tetrahedron. You know how these tetrahedra fit together to give you the figure-8 knots, and so then you can follow through the pattern. That's what this picture is from. This is actually from my own book, which was published last year. But it's due to ideas of Thurston, that you just kind of put the tetrahedra together and you can look it down in them and you can figure out some relationships on the tetrahedra and their shapes, and then you can calculate their geometry. So step 3 is you can determine the geometric invariance from that, and the computer can do this. These are images from a computer program. It's called SnapP. It was originally built by Weeks in the 1980s. This was his mathematical PhD thesis at Princeton University. He built a program that would take a knot as input and it would give you back all of these geometric invariants. Okay, it's now maintained by Culler and Dunfield and Gerner. This is the same Gerner who did this inside view. the figure 8 knot that we saw earlier. Okay, so again, these are very cool, very pretty invariants. And the computer can do this for many, many knots. Unfortunately, a computer can only do finitely many things. It can't do infinitely many things. But it's really helpful for examples that you have. So for example, I mentioned earlier that these two knots found by Purcell to be the same. There's some mix-up as to which knots they actually are. As I was preparing these talks, I typed the two that I found into my computer just to double check that these really were the same knot. And the computer gave me the same geometric structure for both of them. And so I do know, in fact, that these are the correct Purcell pairs. Okay. Okay, let me switch topics again. New invariant. Another way of telling knots apart is using braid groups. So a braid is another group. This is, remember, from abstract algebra, a group is a set that has multiplication and has inversion. And braids are made up of pictures like the following. You have a bunch of dots at the top, you have the same number of dots at the bottom, and then you connect the dots. You have to connect them monotonically. You don't allow any minima or maxima. They have to go straight, all of your lines go straight down, but they can cross. And that's an example of a braid. We can multiply the braids, and the way that we multiply is we just stack them. So this is one braid, this is another braid. Put these two lines together. So right, draw a line, connect these here, here, and here. You get a new braid. The new braid, just this strand follows, ends up there. See, here it is. This strand goes this way and ends up here. Right, so hopefully you can see that this multiplication has given me a new braid. We also need to be able to invert elements. That's kind of shown by this other example. Over here, when you invert elements, you just switch the crossing around. So when you stack these two braids, this strand goes here and then backwards. That's a Reidemeister 2 move. Same thing, here and backwards. The Reidemeister 2 move, this undoes that crossing. So this is not showing an inversion, but over on the left side, we've got the inversion. Anyway, hopefully that'll be enough to convince you. This is a group. Again, we can use abstract algebra to study them. And these were studied in the 1920s by a French mathematician, Émile Artin. Also in the 1920s, Alexander, not the same Alexander from the beginning of the talk, but a mathematician named Alexander, he was able to show that all knots can be written as a closed braid. So this is a closed braid. You've got your braid here, and then you just wrap the strands around the edge and close them up. Okay, and Markov in the 1930s, he showed, or he figured out what closed braids will represent the same knot. But then, so there was this work in the 20s and the 30s, but these kind of fell out of favor. They weren't used, braid groups weren't used very much for a long time after that. One of the reasons that they didn't work well in knot theory is there are just so many different ways that a knot can have a diagram that is a closed braid. And so you really, it didn't feel like you were getting much from it. So entered the scene, I want to say a few words about Joan Birman, who wrote her first paper on braid groups in 1969. So this was several years after this. Joan has a really interesting story. I found an interview of Joan Birman as I was preparing this talk. She was asked, how did you get interested in braids? And she had gone back to mathematics. She had been working in industry, and then she took some time off to raise her children. And then she decided to take a few math classes just to catch up so that she could go back to work in industry again. And she really liked it, and she just kept going, and she decided to get a PhD in mathematics. And one of the requirements for getting a PhD in mathematics is to pass a language exam. And you had to be able to read and understand a paper in French, in her case. And she pulled out Émile Artin's paper on braids, and she read it in French. And so this language exam is what made her really fascinated by these braids, and she decided she was going to write a dissertation on that. And not very many people were thinking about braids in 1969, but she kind of opened up the subject again. There was an article surveying her work in the Notices of the American Math Society in 2019. And this picture came from that article. It shows her influence in various subjects. So she started with braids, that influences knots, surfaces, three manifolds we haven't talked about much, but so she was quite influential and had a lot to do with knots and braids. Okay, that's actually all I'm going to say about braids for a minute, though. I'm going to jump to a new invariant. So completely new invariant, completely new topic. Knot polynomials is the last invariant I want to talk about because these have been really quite useful in recent years in classifying knots. So a polynomial invariant for a knot, what you do is you have this function, you put a knot into it, and it gives you out a polynomial. This is another area that my son told me was kind of confusing. So I'll try and walk you through it a little bit. The example we're going to look at is the bracket polynomial. You're going to plug, you see, we have this bracket here, and we're going to plug in a knot, and we're going to get out a, not quite a polynomial, but a Laurent polynomial. It's possible to have negative powers. And our variable we're going to call A. All right, so what this is saying is if you plug the unknot into this bracket, you should get out the polynomial 1. But then the polynomial is defined recursively. If you plug in a diagram D along with the disjoint union with an unknot, and you plug it into this bracket, then the instructions say, well, just take the bracket of D and then multiply it by this Laurent polynomial. So here's your variable, negative a to the negative 2 minus a squared. That's a polynomial on the outside. And then finally, if you plug in a bit of diagram that has a crossing, you get out the same thing as if you had taken a times no crossing. You take away the crossing in this direction, or a inverse times taking away the crossing in this inverse, or in this direction. All right. This interacts with Reidemeister moves. It doesn't quite work. It doesn't quite give the same thing on the kinks, Reidemeister 1 move, but it gives you exactly the same thing on Reidemeister 2 and 3 moves. So I have a couple of examples. It really, you kind of have to go through them more carefully, but just the idea is if you're given an example like this, there are 2 crossings. We're going to look at the crossing over here on the right first. And my instructions say the polynomial I get from this, when I plug this into the bracket, I'm going to change this crossing in one way and multiply by a, and then I'm going to change it in the other way and multiply by a inverse. And then I look at what's left over, and all right, I'm going to have one more crossing over here and one more crossing here, and I do the same thing, and I get out the polynomial negative a to the 4th minus a to the negative 4th power. And so then you can do this with, there's the trefoil, we've seen that before, you can plug that in and you get out a polynomial of the form a to the minus 7 minus a to the minus 3 minus a to the 5th. Again, this is a Laurent polynomial. So then you can define from this what is called the Jones polynomial. This is named after Vaughan Jones, who unfortunately passed away last year. He is a New Zealand mathematician. But he defined this polynomial in 1984, and one way you can define it is you take your bracket polynomial, and then because the Reidemeister 1 move didn't work, to make this become a knot invariant, you've got to multiply by this extra factor of a determining on your diagram. And I should say as well, this isn't really the way that Jones described it. This is another mathematician, Lou Kaufman, was able to re-describe it in terms of this polynomial. The original formulation from Jones was that you take a trace of a representation into an algebra arising from statistical mechanics. It's very, very, very complicated. But what he was looking at braid representations. So he had this new braid group, this new way of looking at the braid group. And somebody told him, if you're looking at braids, you need to go talk to Joan Birman from 2 slides ago. So he did. He went and talked to Joan Birman, and Joan said, well, a braid representation is cool, but what would be even more cool is if what you had was a knot invariant. Do you have a knot invariant? So they sat down together and he showed her, and in fact, it was a knot invariant. And then they thought, okay, well, surely this is a knot invariant we have seen before. And they plugged through some examples and they realized this was a totally, completely new invariant. And not only was this a new invariant, but it ended up being a very strong, very powerful invariant. It's easy to compute and actually distinguish a bunch of knots that we didn't know before. So one major consequence of the Jones polynomial that came out of it is there had been this conjecture that was implicit in Tate's work. So back in the before the late 1800s, Tate had been assuming in all of this work that he did that if you have a diagram of a knot that is alternating, then it's going to have fewer crossings than the same diagram or the same knot, but with a different non-alternating diagram. So this is just an example here. So alternating means it goes over, then under, then over, then under, and so on and so on. Non-alternating, it goes over and then over and then over and then under and then over and then, right? So this is non-alternating. And you'll notice this guy only has 4 crossings, but this one has 6. And this seemed to be a pattern. It seemed to always hold. Nobody had been able to prove this. For 100 years, this has been an open question. And when the Jones polynomial came out, they were able to show, this was Thistlethwaite and Murasugi, that if you have an alternating knot with n crossings, then the difference in the maximum degree and the minimum degree from the Jones polynomial is equal to the number of crossings if it's alternating, but it's strictly less if it's non-alternating. So putting these two statements together gives you this 100-year-old conjecture. And what a crazy roundabout way of proving that, right? Okay, so I'm about done here. But one thing that you may ask is, so what else is knot theory good for? I mentioned that the reason Tate was interested in knots is he thought he was building a periodic table of the elements, but it turns out he wasn't. Knots are not knotted vortices in the ether. However, mathematicians, they thought this was fun anyway, and they kept going. Well, there are a lot of modern applications to knot theory. These appear in physics, in DNA, in protein folding, in chemistry. I just have a couple of pictures. This came from an article called Knot Theory in Modern Chemistry by these people in the Chemical Society reviews. This is a picture of an example of knots appearing in chemistry. So technically, these are colloidal spheres held together by disinclination defects in a chiral pneumatic liquid crystal. I don't know what any of that means, but I see the knots. Okay. Knots appear in DNA, in replication. Mariel Vasquez is a mathematician in the US who has been looking very carefully at knots and how they affect DNA, and she has a lot of work on that. This is from an article that she wrote in August 2018. Okay, so those are just a few highlights of some of the ways that knots are used today. There are still many open questions in knot theory, and here are a couple I identified that you may have picked up from the talk. How good of an invariant is the Jones polynomial? We still don't know. So no one has been able to find an example of a knot which is not the unknot and yet has Jones polynomial 1. So question number 1 is a big open question. You can prove this. This would be quite impressive. So if the Jones polynomial of a knot is 1, must it be the unknot? Question number 2 is related to this universe picture that I had. Is there a better algorithm to decide if a knot is the unknot? Okay, we shouldn't have to take several ages of the universe to determine if a knot is the unknot. And then my final slide just is a follow-up on this. I mentioned this tweet from Oxford. In February of this year, Mark Lackenby at Oxford announced that he found an algorithm to determine if a knot is the unknot, but now in quasi-polynomial time. So this is n to the c log n steps. This is significantly better than this number of Reidemeister moves. And these pictures came from their Oxford Maths announcing this, in which they claimed was the unknot. And so Mark's algorithm is going to make it possible to tell definitively in a reasonable amount of time. So thanks very much. And I will stop there and look at your questions.
Thanks very much, Jessica. Okay, so there's quite a few interesting questions here. So we've already answered a couple of them. All right, here's a good one. Is there a relationship between the number of crossings and the number of knots with that many crossings?
Okay, yeah, that is a good question. The relationship between the number of crossings and the number of knots, it grows exponentially. So this is kind of related to this classification. Let me scroll way up. These pictures, right? We started with small numbers, and then they grew and they grew and they grew and they grew. There are bounds on the numbers of knots that you would expect with the number of crossings. We know for the examples that are known, they grow exponentially. In 2019, Ben Burton at UQ classified all knots up to 19 crossings. This is as far as we've gotten. There are 350 million of them. So we know that the number grows exponentially, but we don't have an exact relationship about how many there must be with a particular number of crossings. That's a hard problem and takes a lot of compute time to be able to answer.
So do you know the rate of the exponential asymptotically?
I think that there are bounds. I don't know them off the top of my head, but yeah, I think there are bounds on that.
Okay. So here's another good one. So you mentioned we have an algorithm to determine if a knot is equivalent to the unknot. Can we tell if knot A is equivalent to knot B with a similar algorithm?
Yes, that is a very good question, and the answer is yes. So I probably should have said that. Following the work of Haas and Ligarius, a bunch of people looked at similar questions, and so two names that should come up would be Alexander Coward and Mark Lackenby. This is the same Lackenby in the last slide. They came up with a count on the number of Reidemeister moves needed to determine if two given knots are the same knot. And it's a hilariously huge number. But so you can do similar things for a similar problem. So yes.
So the next one, any book recommendations, particularly on knot theory and abstract algebra?
On knot theory and abstract algebra. So that's a good question. I probably would recommend just to start with, I really like Dale Rolfson's book. I've mentioned Rolfson. His book was published in 1976, and one of his chapter number 3 is all about knot groups. That's where I got these pictures. If you haven't seen a lot of abstract algebra, it probably would be better to just start with an abstract algebra book, perhaps, to look at that. Colin Adams also has a really great book that's quite accessible on knot theory, although he starts more with the polynomial invariants and some of the DNA and chemistry applications. And I don't know if he spends so much time on the abstract algebra aspects of it, but I do believe he talks about it a little bit. So just for the knot groups, I like Dale Rolfson's book, Knot Theory, I think is what it's called. Knots and links, Dale Rolfson, Knots and Links. And if you are interested in just more general knot theory, Colin Adams has a book. And if you're interested in hyperbolic geometry, you can go look at my book on hyperbolic knot theory as well. Yeah.
This one's probably a little bit hard to answer, but the question is, are some knots better or more powerful in some sense than others in some applications?
So I don't know about better or more powerful. It seems that in most of the applications we've looked at, the smaller knots are the ones that are appearing more frequently. So in these chemistry applications, for example, there's the trefoil. This is actually has 2 components, so it's called a link rather than a knot. But you can see that we've got small examples from the early knot tables, not very many crossings. In a DNA, this isn't from an electron microscope. This is a trefoil again, 3 crossings. So these sorts of things appear. I don't know if that's necessarily because they have more applications or better applications. It may just be that these are really, really hard problems, and these are the ones that we're able to solve, are the ones with very few crossings on them and not as high of complexity. And that's kind of where we are, I think, in terms of the research.
Okay, we've got time for another couple at least, I think. Are knots in higher dimensions than 3 interesting?
Are knots in higher dimensions than 3 interesting? Yes, star. Depends on how you define them. So if you look at a circle, embedded in 4-dimensional space, it turns out that you can remove all of the crossings just by stepping into that 4th dimension. So circles in 4 dimensions, everything is equivalent to the unknot. However, if you take, instead of a circle, if you take a sphere in 4 dimensions, then you can get all sorts of crazy knotting happening with your spheres. And so there are people who look very closely at two-dimensional spheres knotted up in 4-dimensional space. And there are a lot of open questions on that. Similarly, it's codimension 2, if that means anything to you. If you are in dimension n, look at the spheres of dimension n-2, and those give you the most interesting knots and the most interesting problems.
So this is maybe not a fair question because you're not a mathematical physicist, but are there any applications to string theory?
It is a fair question. It's a good question. I'm not a mathematical physicist. So I don't actually know the correct answer to that question. There may be, but I don't know.
Is there a theory of random knots?
That is an excellent question. Yes, there is a theory of random knots. There's lots of modern research on random knots and what that means. Just glancing at the question, you've also written there, if so, what sort of distribution would you put on what? That's the big question. How do you enumerate knots? There are lots of different ways of doing it. If you just say, I'm going to pick a random knot with however many crossings, then there are ways that you can build this. So Nathan Dunfield, for example, has looked at random knots where you enumerate based on crossing number. But there are other ways of thinking about knots. You can build them out of, there's a petal number, there are grid diagrams, there are twist numbers. And if you build random knots in different ways, you get that your generic knot has different random properties. So yes, there are lots of very interesting questions about random knots, active area of research.
Is it true that minimal crossing knot diagrams must have alternating crossings?
Oh yes, this is a good question too. And this I should clarify. So this result on the Jones polynomial, if you have an alternating diagram, then that one has minimal crossings. Not every knot has an alternating diagram though. So Tate originally thought that every knot was alternating. So let me go to Tate's picture. You can see he hasn't given any crossing information here. It's because when he originally started classifying knots, he just assumed that they all could be made over, under, over, under, over, under. They can't. The first example of that, all of these are alternating. The first example of a non-alternating knot has 8 crossings. Let me see if I can find one. So some of the higher ones with 8 crossings are non-alternating. 819, for example, is non-alternating. You can see here, you go under and then under. And I think early knot theorists spent a lot of time thinking, oh, I've got the wrong picture. I got to keep rejiggering this thing until I get something alternating. You can't. You can use the Jones polynomial and other polynomial invariants to prove that knots have no alternating description. Yeah.
Okay, we're almost at time, but there's one more here that would be a good one to end on. Do you have a favorite knot?
Do I have a favorite knot? Yes. My favorite knot is the figure 8 knot. The reason that is my favorite knot is because of the hyperbolic geometry. This was the knot that kind of got me into knot theory. This picture here, just writing the knot as 2 tetrahedra, spreading the tetrahedra out, and then finding this beautiful pattern and symmetry in this structure, I think is just really, really cool. And this is simple enough knot that you can actually do this by hand on paper at home by yourself. You don't need the computer. So that's my favorite knot.
Okay, great. Well, thank you very much, Jessica, for a really interesting talk.
All right, thank you.